As Stephanie mentioned, over the last couple of months, SAGA has hosted a number of talks on hydrogen from international participants, and the message that I got from listening to a handful of those talks was that across the globe, people are finding more and more natural hydrogen and are considering whether it might be a sustainable source of clean energy. And largely they've been saying, why don't you look for it in South Africa? It's got a lot going for it. So my talk here this afternoon is very much to complement those because we have been looking here in South Africa, and it's those results that I want to try and share with you. Yeah, so I also need to do a bit of a plug here for our various sponsors and the umbrella organization that we are under. This project is called High Africa, and it falls under an organization known as LEAP RE that you can see in the center of the screen there. And that's a fairly lengthy acronym, but you can see it written below there, long-term European Union, African Union Partnership for Renewable Energy. So what they basically do is put together European partners, European academic institutions and African academic institutions to get us to all try and work together. And we all have to find our own local source of funding. And in this case, down on the bottom left, the funder of the South African branch of our High Africa project is SANEDI, also another lengthy acronym. That's the South African National Energy Development Institute. So we're partnered with some European organizations, Converge, which is in the University of Évora in Portugal, LIAG and Fraunhofer, both in Germany. And here in Africa, we've got partners in Mozambique, at the University of Eduardo Mondlane, partners at the University of Togo, and partners at the University Mohammed Premier in Morocco. And here in South Africa, there's us and the University of Limpopo working together. So we're in those four African countries, we're all looking independently at our own countries to see if we can't find natural hydrogen. When I call it natural hydrogen, you also might see it referred to in the literature as white hydrogen or gold hydrogen sometimes. And another term that's been used, which I quite like, it's a little bit more descriptive, is geogenic hydrogen, implying that it's made by the geology, and that's exactly what we think is happening. So our original idea was to try and find if there were areas of natural hydrogen accumulation which could be used for small standalone renewable energy solutions. And later on in the talk, I'll show you an example of where that is being done here in Africa. So, as you're likely aware, hydrogen in general is being proposed as a way of contributing significantly to the global energy budget. The problem is it with hydrogen is that it's terribly expensive to produce, or it's not terribly good for the environment. So if you're producing hydrogen by steam methane reformation, you've got to have natural gas or coal. And you can produce what's known as grey or black hydrogen, or if you manage to store away the vast amounts of carbon dioxide that's produced by that process, then you call it blue hydrogen. A cleaner solution to this is to use green hydrogen, which is where you're using wind energy, solar electricity to electrolyze water, split the hydrogen off from H2O. And then you produce green hydrogen, but that is very expensive. You can see at the bottom there in the green box, about between $2.5 and $6.5 US per kilogram. Schedule or hoped that that price will come down by 2050. But then if you look at natural hydrogen on the right-hand side there, the great thing there is that all of that energy that's required to split hydrogen off from water is supplied by either geothermal energy or by naturally occurring radiolysis in granitic rocks. And you can see the price is expected to be sort of around and about $1 per kilogram of hydrogen. So a considerably cheaper way of producing hydrogen if it's all done naturally. You'll just have to collect it. So let's now skip to South Africa and a bit of a historical perspective on the Highveld. Anybody who's driven along the N4 or through the sort of Hendrina area will have likely noticed all of these pans across the Highveld. Very strange features, and there's been fairly lengthy discussions over the last 70, 80 years or so about what the geological factors might be that have caused these pans. So here you can see a map from 1955 from Wellington. They're obviously aware that these required a bit of an explanation. And the idea up until now was that these pans were represented former drainage lines, old river courses that as Africa has tilted in the geological past, these rivers have basically become choked with sediment, stopped flowing so strongly, um, and resulting in these sort of lines of oval shaped pans, sometimes lining up, but all pretty much parallel to each other. And these former drainage lines, the argument is that as animals come in to drink, that the hooves, the footprints of those animals kick up the dust and the dust blows away. So you get deflation occurring. And this has pretty much been accepted. Whether you think it's convincing or not, I'm not sure. But these are the what we've been looking at. And the reason that we focused on these pans is that if you look at other reports that have been growing almost monthly in the international literature, where there's been reported occurrences of natural hydrogen, most of them have been associated with these things that sometimes they call them fairy circles. Sometimes they're a little bit less esoteric and they just call them subcircular depressions. And you can see a couple of examples of this on the right-hand side. That top one is in Brazil, and there's quite a noticeable reduction in vegetation as you approach that fairy circle. The bottom one, which is a LiDAR image just to highlight the size of the subcircular depressions there. They're in South Carolina. And you can see that these are shallow depressions from the different color in the image there. And interestingly for me, they're all oval. And the long axis of each of those elliptical shaped depressions, they're all parallel to each other. And again, this is somewhere where it's been known for the last 5 years or so that there is anomalously high surface hydrogen. So our idea in High Africa was, well, that looks very, very similar to what we have here in Mpumalanga. We call them pans. In Carolina, they call them Carolina bays. But they are really very, very similar. Notice that here in Mpumalanga, we've also got those elliptical shaped depressions, in our case, filled with water very often, although they do dry out in the middle of winter, some of them. And those long axes are all parallel, and many of them do line up, one after the other, all along a single lineation. So these, instead of being linked to drainage patterns of the past, we wondered if maybe these were hydrogen bearing. So that was our main aim in the High Africa project, to go out and just measure around the edges of these pans to see if they were similar to the hydrogen occurrences around the edges of fairy circles reported internationally. So we started this about 2, 3 years ago. So that's our field area. On the left, just a sort of provincial map, and on the right-hand side, you can see that that our study area is located pretty much exclusively on the lower part of the Karoo supergroup, on the Freiheit formation of the Eka group. And this is our very straightforward and really quite cheap field methodology. This is the equipment that we bought, and we got it pretty much off the shelf in a variety of different stores. You can see our big yellow drill there. That's just a handheld battery-operated drill. It's the sort of thing you might have in your shed if you're seriously into DIY, maybe sort of light construction industry. It's a pretty serious drill, but it is handheld. And at the bottom there, you can see a meter long 15mm drill bit. And we use that just to drill a meter long hole, 15mm wide, down into the soil. And that helps to release any soil gas that might be present in that top meter. What you can also see in that image is a hydrogen meter. That's that orange colored box with the screen, and then that's connected with a pipe to the probe that gets stuck down the hole that you've just drilled. You can see that on the right-hand side in the process of recording a hydrogen reading. And again, this equipment is pretty much off the shelf, although it is a bit specialized. This particular hydrogen meter comes from the plumbing industry. And if there's a leak in a pipeline, the idea is that you vacate whatever it was that you were piping through that pipeline and use bottled hydrogen to fill up the pipeline, and then you probe along above the pipeline in the soil above the buried pipeline until you find a high hydrogen reading, and that's presumably where your leak is. So yeah, we just bought this from a company in Johannesburg off the shelf, and they supply these to plumbing companies involved in leak detection. So not terribly expensive equipment. This whole setup cost us less than 20,000, sorry, less than 200,000 rands. And this is what we use to measure for the presence of hydrogen in the soils. Ordinarily speaking, the present hydrogen in the atmosphere and in surface soil shouldn't be more than about 0.5 to 1 part per million. So that would be a typical reading. If we wave this machine around in the atmosphere or in a normal soil, if you like, then you shouldn't get much of a reading at all. So these are the results that we've got. You can see that there's a set of diamonds that have been put over this Google Earth image, and you can see a main road there going between Middelburg and Hendrina running down the center of that Google Earth image. And if you look at the size of those diamonds compared to the legend on the right-hand side, just driving along the road and recording hydrogen concentrations on the road verges, it's all a bit disappointing. Generally less than 2.5 part per million, which is, yeah, maybe slightly elevated above what you'd ordinarily expect, but not amazingly so. And you can see there's a few pans around the Hendrina area. That town in the bottom center south center is Hendrina. But if you look at some of the pans that we've measured, the size of those diamonds is getting really big. We've got often tens, sometimes 100s, and on occasions thousands of ppms around the edges of those pans. So as we predicted, as we hoped, these pans do indeed seem to be related to an increase in hydrogen around the edge of the pans, just like the international examples have shown us. Maybe just zooming in on that pan just to the northeast of Hendrina there. Obviously, our symbols stay the same, but you can see some of those really big readings that we've got, hundreds and in every now and then thousands of ppm of hydrogen. Often it's very difficult to predict where the high readings will be. If we've had a high reading of 1,000 or so ppm and we come back a few hours later, then it's back down to more normal levels. And in other areas where we've had fairly low readings, we might go back again and suddenly it's high. So we've found it extremely difficult to try and predict the periodicity in which we get high peaks of hydrogen. In other parts of the world, they found a great deal more periodicity. They find that overnight the hydrogen levels drop, and then during the day, as temperatures increase, that's atmospheric temperatures increase, then hydrogen tends to go up with daytime temperatures. We've tried doing readings at night. We've tried doing readings at various moon phases, wondering if, like tides, if the moon's gravitational pull might be helping to suck high hydrogen out of the ground. We found no patterns whatsoever. So it seems to us that the hydrogen is coming out as burps every now and then in certain locations around the perimeter of pans, but it's a bit hit and miss exactly where that hydrogen does come up and when it comes up. And that seems to be mirrored in some of the literature internationally as well. People have noted this very poorly constrained periodicity in when the hydrogen might come up to the surface. But nevertheless, the very high ppms of hydrogen that we've been getting, which are on par with other potential hydrogen reserves internationally. These are extremely comparable, if not even more so. And in one place, this is out much, much further to the east near Chrissy's. We found one location which has been producing 45,000 ppm. That's the highest we've ever got, but that really is quite staggering. When you consider it should only be about zero point 0.5, this is 90,000 times more than the background level. So there is definitely some sort of naturally occurring hydrogen beneath this the high felt pan field that's leaking out to the surface through the soils in alongside these pans. So having established that there is something going on that accounts for the presence of the pans, they do seem to be just these subcircular depressions, very similar to what people have found elsewhere in the world. What could the geological controls on this be? Why the hydrogen? Well, lots of interesting factors to try and explain, and I'm not sure I can fully explain much of it, but I can, we can do some pretty good guesses as to what might be going on. The first thing that I want to point out here in terms of the geological control is that there's this very, very close coincidence between the presence of pans and therefore presumably the presence of hydrogen and the Ecker Group rocks, the Freiheit Formation. You can see in that, well, it's sort of shown to some extent on the diagram on the map on the top left. That's just the usual Council for Geoscience maps, and each of those red dots that you can see are the center of pans. And notice that as you come off the Ecker, they pretty much disappear altogether. One or two exceptions. I think you've got to bear in mind that there's very, very little outcrop in these areas. So the mapped edges of the Ecker, where you pass through the unconformity into the Precambrian rocks, is not terribly clear. And I suspect that many of the pans that are mapped off the edge of the Ecker might indeed still be on it. It's just that the map's boundaries of the Ecker aren't very clear. That's also highlighted in that map on the bottom right there. We've cut out a bit of the noise. My co-author on this talk, Ansi Smith, prepared this. So in green, you've got the usually Precambrian rocks. It's everything that's below that unconformity below the bottom of the Karoo supergroup. And in pink, that's the Dwicker and Ecker. And you can really see the close coincidence between those pans, which is that rash of blue colors scattered across the map there. There really are thousands of them. And the very close coincidence of those with the Ecker group. So that's something that needs to be explained. Another interesting fact is the way that these pans, these subcircular depressions, are elliptical in shape, and the long axis of those ellipses are often parallel to each other. So we've tried to highlight that with this map. It shows each of the red lines is showing the orientation of the long axis of those elliptical pans, and it really does highlight how nicely parallel they are, and sometimes all lined up one after the other. And the other interesting thing is if you look at the local geophysical lineaments that are plotted on the Council for Geoscience maps, they're the black dotted lines, and they're closely parallel to those as well. There's a little rose diagram on the right just showing the pan orientation, and you can get some impression about the orientation of the lineaments as well just from looking at the map. And there does seem to be some relationship between the pans and the lineaments. And the old model of drainage derangement wouldn't really take those lineaments into account too much, or the parallel arrangement between the pans and the lineaments. So we think there is some control there. We're starting to look now at the possible relationship between not just those geophysical lineaments, but joint orientation. This is the big pan at Chrissy's Mere. This is a huge one, probably the biggest pan that there is in the entire panfelt. Very often there's no outcrop whatsoever, which makes this sort of analysis very difficult. But the pans in the Chrissy's Mere area do at least have some outcrop around them, which often interferes with the perfectly elliptical shape. You can see that the Chrissy's Mere pan is sort of deformed into a weird sort of embryo/kidney type shape. And the reason for that is that the Freiheit Formation in this particular area is a little bit more indurated, and so there is a bit of outcrop. So that red box you can see on the Google Earth image, I've zoomed in on that to the point where you can very nicely see the dominant joint patterns in there, and the strike of those joint planes seems to be at least roughly coincident with the orientation of the pan. So I think that might well be a control, but we need to do a little bit more work on this. Um, so going on then, still sticking with this idea of what are the geological factors that might be controlling and producing the hydrogen in the first place. There's two dominant ideas in the literature about where natural geogenic hydrogen might come from, and the most popular one is serpentinization. That's where the vast majority of geogenic hydrogen is thought to be produced by from mafic and ultramafic rocks with iron-rich olivines, fayalite, and orthopyroxenes. If they can be buried to sufficiently great depth, they need to be at about 200 to 300 degrees centigrade to start driving these reactions. So that's going to be about between 5 and 8 kilometers of depth, depending on the geothermal gradient. If they can be at those depths and subjected to plenty of flushing with water to get those serpentinization reactions going, then you can potentially produce hydrogen. Unfortunately, my little red oval there, which is meant to be centered on the southern lobe, seems to have shifted, and I'm not sure why. But we have right under our field area the southern lobe of the Rustenburg layered suite, which has iron-rich olivines in the upper zone. So that's directly below our field area. So that might well be the source of our hydrogen. The idea is I don't even pretend to understand the complexity of serpentinization geochemical reactions, but basically you add an OH onto the mineral equation, and there's a spare hydrogen from water that then would come up as molecular hydrogen up to the surface. So that's one obvious smoking gun as to where the hydrogen might come from. This is gravity also showing, you can nicely see the eastern and western limbs that outcrop perfectly, and then that big anomaly to the south, which is within that pink colored box. That's the buried southern limb. And you can see each of those dots that you can see there is one of the pans that we've plotted on top of it. And there's obviously a pretty close coincidence between that buried southern limb and where the pans are. But interestingly, it's not exclusive. If you go to the east and the west of the greatest part of that anomaly, where there are clearly no bushveld mafic rocks, and we still have pans and we still have hydrogen. So this only goes some of the way towards explaining the pans that we have at the surface and the flux of hydrogen at the surface. Another interesting point is that the southernmost parts of the southern limb that you can see towards the southern part of this diagram, that's at really a very shallow level. So although there may be mafic rocks with the right chemistry, they are probably insufficiently deep to have that elevated temperature to start serpentinization. It obviously dips northward, so as you go north, they would attain the correct sort of depth, but notice that the pans seem to peter out. So it's possible that any hydrogen produced further north at depth is transporting northwards, going up dip, and then appearing at the surface further south than where it's produced. That's a possibility. But it still doesn't explain the considerable production of hydrogen to the east and to the west of where the southern limb is. So are there any other ideas? We're actually a bit spoilt for choice as to what it might be. Again, that red oval is the area where we're looking, and you can see from this geological map, just up to the northeast from there, you've got the northeast southwest trending Barberton greenstone belts. Greenstones are also thought to be a great source of serpentinization. Many of the greenstone belts are already serpentinized, including Barberton, but many people have seen coincidence between buried greenstone belts and hydrogen production. So maybe there's enough non-serpentinized material still sitting in these greenstone belts that if they get sufficiently deeply buried, that they will continue that serpentinization that began way back in the Archean. And yeah, if you continue that long axis of the Barberton greenstone belt, it does go right underneath the our study area. And there are various other little greenstone fragments that are cropping out between Barberton and our study area. So it's plausible that there might be greenstone material sitting in the crust below that unconformity with the Eka. Of course, the other way that hydrogen is produced that I haven't talked about so far is by radiolysis. So what you really need to start splitting hydrogen off from water for radiolysis is uranium, potassium bearing granites. And so what many people internationally are looking for are Archean age TTGs. And of course, we're not short of those in this area either. All the way around the Barberton Greenstone Belt, you've got those TTG deposits. So they are likely clicking away, releasing alpha, beta, and gamma particles, all of which could split hydrogen off from water by radiolysis. There are other mafic rocks as well. There's the Pongola supergroup. You can see that down here in the southwest corner. That disappears along strike underneath our study area. So the take home from this is there are plenty of reasons why we might be getting hydrogen produced, whether it's by serpentinization of a number of different mafic rocks, whether it's by radiolysis. We're spoilt for choice as to what might be producing this hydrogen. And maybe it's several different factors all happening by chance to be coincident under our field area. Just by way of comparison, the one place in Africa where natural hydrogen is actively being exploited is in Mali. It's a very difficult place to visit. I've certainly never been there. I've talked to some people who have been there, and it is real. It's pretty well documented now. What happened there was they were drilling a water borehole, and they got to just beyond 100 meters. And apparently one of the drilling contractors was a smoker, discarded his cigarette, and the whole drill rig went bang and caught fire. They managed to get the fire out. And they are now exploiting that hydrogen. It's apparently 98% hydrogen. That's a percent, not a ppm. And so they route that hydrogen from the borehole into the collecting tank that you see in the image on the right-hand side. And then they just tip that through the carburetor of an ordinary petrol engine. And it burns, and water drips steadily out of the exhaust pipe instead of any carbon dioxide. And that engine then powers a 30 kilowatt generator, and the local village gets free electricity. So this is the kind of model that we were hoping might be applicable to local communities in the Mpumalanga area or in any of the other areas that have been examined by the High Africa Project. So the geology of this area really is very reminiscent of our situation in Mpumalanga. This is from a paper that was produced last year, Hutchinson et al., 2024. The location of this Mali occurrences in the Tawadeni Basin, which is a bit older than the Karoo, but nevertheless, you can see that it's sitting unconformably, as the Karoo is, on top of Archean-aged greenstones and granites. The greenstones are nicely picked out in green, and you can see them just disappearing under that unconformity and presumably continuing towards the northwest, directly underneath that red star, which is where the Burakabogu locality is. So they think that's the source of the hydrogen. It's getting up to a shallow level, and then at about 100 meters, it hits a sill. And that sill seems to be acting as a trap, very akin to petroleum geology here. And you have a kitchen depth, and then just like natural gas would rise up to the surface until it hits a trap, and below that trap you get a reservoir. All the same terminology is now being applied to hydrogen reserves. So in this case, that sill at 100 meters has seemed to act as the trap, and when the those drilling contractors punctured through the bottom of that sill, that's when the hydrogen came up. So we don't have the sills in Mpumalanga setting in the areas where we've been looking, but we seem to have pretty much everything else. So you could argue that maybe we don't have such a good trap. And the I would think that the large number of pans, all of which seem to be characterized by the surface flux of hydrogen, might be indicating that if there is a trap there, that it's a pretty leaky one. The more it would leak, the more hydrogen would come up to the surface, and the more pans you'd get developing. So maybe we're just sitting on a leaky trap there in Mpumalanga. Interestingly, as you go to the south, you stay on the Freiheit Formation, but you also pick up a lot more sills. There's that map in the top left of the image that we showed before. And notice how, as you get south of our study area, the frequency of those pans really drops. And the reason for that is that we're getting on to Karoo dolerites. So we sent a student last year down to go and look at those, some of the few pans that are developed close to the edge of those dolerites. You can see there's those three little geological maps that show pans close to the edge. And the results were very disappointing. We were quite, well, disappointing in a kind of a nice way, in that it did seem to match what we'd hoped. We were used to getting hundreds or thousands of ppms alongside pans further north, and the highest reading that this honest student managed to get around the edge of these pans closely associated with the dolerites were 34 ppm. So our interpretation of this is that maybe those dolerites, like in Burakabogu, are acting as a better quality trap. The pans are developing, but maybe not developing terribly well, and the flux of hydrogen to the surface seems to be reduced. So maybe that would be a good target, rather than the places where we observe a large surface flux of hydrogen, which would indicate that it's leaking past the trap. Because we've got radiolysis in mind, with all of those Archean age TTGs somewhere way down below the surface rocks. So we've been looking for radon to see if we can establish any link between the concentrations of hydrogen and radon gas. Radon, of course, being a product of those same radioactive decays that might be splitting hydrogen off from water at depth. We have some weak relationships. You can see in the top there at Hendrina, we've got an R value of 0.4, which is a bit of a slightly disappointing, but nevertheless, there's some relationship there. But then in Chrissysmere, which is where we really thought there might be the radiolysis as sort of that hydrogen, there the R value's down to 0.09, absolutely hopeless. So this is actually very unconvincing for radiolysis as the source. We couldn't establish any real connection between hydrogen concentration and radon concentrations. If anything, the only reasonable relationship that we observed is in the wrong place, where we were pretty sure it would be serpentinization taking place. So that's still a bit of an unknown factor. So this is an image that was published in the popular press a couple of years ago, just showing the various ways that hydrogen could be produced and what factors you would need in order to get hydrogen being trapped, and the various surface signs that you could look for to see if hydrogen was there. So you can see the fairy circles that we've been chasing in that box on the top left-hand side. You can see reference to the radiolysis at depth at the bottom left, and serpentinization of olivine on the bottom in the center. So really all of these factors that researchers up until now have been highlighting as being important for hydrogen production, we've got them all in Mpumalanga. So we think that's quite exciting. This is part of our work in just trying to come up with a a list of factors that might be important taking hydrogen further. And what I've highlighted with the red arrow there is the presence of an unconformity. For any of these reactions to take place, whether they're radiolytic reactions or whether they're serpentinization reactions, you have to have that water. And so you need very well-established faults going to a deep level in order for that water to circulate down to those levels where they can react with the rock. On the other hand, at the surface, well-developed faulting is the last thing that you need. We've seen in the earlier slides the relationship between the geophysical lineaments, which might be faults, and the orientation of the pans. To me, that implies that these faults are bringing the hydrogen up to the surface and it's leaking out above where the faults are cropping out. So what you would really need is a faulted basement to allow the circulation of water and allow for the percolation of hydrogen back up to the surface, but not a faulted trap or cap rock. So the obvious way out of that is to have some sort of unconformity developed where you've got the ancient, deeply faulted rocks and much younger, less faulted rocks at the surface that might be a suitable trap. And that, of course, is exactly what we saw at Barakabogu, and that's exactly what we have in that major unconformity between all the various Precambrian rocks and the Karoo strata there in Mpumalanga. So I think those unconformities are quite an important thing to look for as an exploration tool. So yeah, that's pretty much the end of my talk. I won't bother going through each of the conclusions individually because we've discussed them all. But yeah, we're quite excited about what we found. We think we've solved the mystery of where the pans might come from. We think they're all hydrogen related. Whether or not this is going to turn out to be an exploitable resource or not, I don't know. The frequency of pans would suggest that a lot of this hydrogen is leaking out into the atmosphere, but maybe focusing efforts on the areas underlain by the dolerites further south might well be a better exploration model. What else have we got? There's a few references, and